Now the next model uses something which is called as the fixed point shifting, and it'll be used in the functional equations which have f ax plus b, that is when a function has an affine map ax plus b. Now if we take this map as tx, which is ax plus b, then t square x will be ax plus b, and there'll be a square x plus ab plus b. T cube x will be a cube x plus a square b plus ab plus b. And there is a structure here. This t and x, it is a to the power nx plus b, and this is a to the power n minus 1, a to the power n minus 2, plus a plus 1, which is gp, t n x, a n x plus b, and it will be 1 minus a to the power n upon 1 minus a when a is unequal to 1. But here with every iteration, there is a change in the constant term, and therefore using it in a functional equation, it becomes a hassle. Now against this, consider this map tx equals ax. Now here, x, it simply scales to ax, it will scale to a square x, and it will keep scaling up to a to the power nx. Now this is very simple as compared to this transformation where this x, it undergoes scaling and then shifting. So it has both scaling and shifting. And since scaling is simple, the entire point of this model is to find a fixed point about which this affine map, it simply transformed to scaling. So that's the basic idea behind this model. Now the first thing that we need to know here is how to find the fixed point. So every affine map tx equals ax plus b, where a is unequal to 1, it has a fixed point, and this fixed point is given as ts equals s. So we write s equals as plus b, or this s will be b upon 1 minus a. So this s, it is our fixed point. What we are essentially doing here is we are changing the origin to this point s. So previously, which was input x, is now this input u in this new origin. Then from here we can say this u is x minus s. So this is how your input changes when we change the origin to the fixed point. Now, if you want to look at the output, your output will also be changed. So it'll be this tx minus s, and then it'll be this ax plus b minus s. Now b minus s is as. So we can write this as a x minus s. So this output tx minus s, it has become pure scaling. So these are the two things that we'll need in functional equation questions containing affine input. Now the working algorithm for this method is, first, find the fixed point. By setting ts equals to s, and we let u as x minus s. And second step is we'll shift the function. So we'll define a companion function gu, which is given by f u plus s. And since u plus s is x, so this is basically fx equals g x minus s. We'll need it in the end when we're going to find fx from gu. We can write f ax plus bs gx minus s. So it'll be this g ax plus b minus s. Now we know that as plus b is s. So this b minus s, it is nothing but it is minus as. So it'll be this g a x minus s, and x minus s is u. So this f ax plus b, it changed to g a u. So say for example, we are given this functional equation f 2x plus 3 equals 4fx for all x belongs to R. Now here we have this affine map. Now here if we take this transformation as phi t and it is 2t plus 3, then phi square t will be 2 into 2t plus 3. So it will be this 4t plus 9. Phi cube t will be 4 into 2t plus 3 plus 9. So there will be 8t plus 21. And this is not a cyclical structure. So we'll never get an identity in this. And finding this function through brute force, it is difficult. So what we'll do here is we'll use fixed point shifting. So first step, we'll find the fixed point. So we'll take 2s plus 3 equals s. It'll give us s equals minus 3. So our origin, we have shifted it to minus 3. And then we'll let us x minus s, which will be minus of minus 3, x plus 3, or x is u minus 3. Second step is we'll change the function. So we'll let gus f u plus s, and s here is minus 3. So it'll be u minus 3. And u minus 3 is nothing but x. So basically, we have taken gu as fx. Now we'll transform this argument. So we have 2x plus 3. We can write this as 2, and x is u minus 3. So it'll be 2u minus 3 plus 3. So it'll be this 2u minus 3. So we can write f 2x plus 3. It will be f 2u minus 3. Now gu is fu minus 3. Then g2u is f2u minus 3. So this f2u minus 3 is nothing but it is g2u. So what you have done is we have changed this function f2x plus 3 as g2u. So this is g2u and fx is simply gu. So it'll be g2u is 4 times gu. So we have reduced this functional equation to pure scaling. And that's what this fixed point shifting does. Now we get this condition, but still from this condition alone, we cannot find a function. So whenever you'll get a question, you'll always get some additional condition with it. So here, suppose in the question it says, this gu is a monomial. So we let gu as c u to the power k. So this left hand side will be c 2u to the power k. It'll be 4c u to the power k. Comparing, we'll get 2 to the power k equals 4 or k equals 2. So this gu will be cu square. Now gu is actually fx. So we'll get this as fx equals cu square, and u is nothing but it is x plus 3. So this function f will be c into x plus 3 square for all x belongs to R under the condition that this gu is a monomial. Here the first question is, we are given that f1 is 1 and fn plus 1 is 2fn plus 1. What we'll do is we'll add 1 both sides. We can write fn plus 1 will be 2 times fn plus 1, and if we take a function gn which is fn plus 1, we can write gn plus 1, it is 2 times gn, that is basically gn is a gp. Now g1 is f1 plus 1, so it will be this 2, and common ratio is also 2, so this gn will be 2 to the power n. Now gn is fn plus 1, so this is fn plus 1, which means here fn is 2 to the power of n minus 1, and this second question we have already solved, and we know that this is 1 minus x square. So answer to this first question is C, and the second question is B. There may be questions where your input may be affine and your output also may be an affine function. Say for example, when we have functions such as f ax plus b is afx plus b. Now here input, it is ax plus b, whereas your output, it is ay plus b. So this is your input map, and sy is your output map. So in this, one shift is not enough. So what we'll do is we'll find fixed points for both input map as well as output map. So the first step is we'll find 2 fixed points. So let the fixed point here is sx. So it will be sx equals a sx plus b, and here will be this sy, and will be this a sy plus b. So this sx will be b upon 1 minus a, and sy will be capital B upon 1 minus a, and here a is unequal to 1, and also capital A is unequal to 1. Now again we'll let u as x minus sx, and for questions where they'll give another equation which contains both x and y, we'll take v as y minus sy. So for this question, we'll not need this v. Now here, we'll define this function gu as f x plus sx minus sy, and everything else will remain the same. So let us take up an example. Say for example, we need to simplify the structure f 2x plus 3, and it is equal to 3fx plus 4. Now input fixed point will be 2sx plus 3, sx equals minus 3, and output fixed point will be 3sy plus 4, or sy is minus 2. Now we let u equals x minus sx. So it will be simply x plus 3, or x is u minus 3. And we'll define gu as fx minus sx. So it'll be f, and this is x plus sx, and sx is minus 3. So it'll be this fx minus 3 and minus sy. So it'll be this minus minus plus 2. So we have defined a companion function gu as fx minus 3 plus 2. Now what we'll do is we'll substitute this x in the original function. So it'll be this f 2u minus 3 plus 3, and this is 3 f u minus 3 plus 4. Now this is f 2u minus 3, and this is 3f u minus 3 plus 4. Now, if we look at this gu, it is fx minus 3 plus 2. So we have minus 3 both sides, but we'll need plus 2. So what we'll do is we'll add to both sides. So now it'll be f 2u minus 3 plus 2, and it'll be this 3 f u minus 3 plus 2. Now this is nothing but this is g2u, and this is nothing but this is gu. So again, it has changed to simple scaling. So this is how we use double shift to simplify the functional equation. Now let us take up an example. It says find all the continuous functions defined on R2R such that f2x plus 3 is 2fx plus 3 and fx plus y plus 3, it is fx plus fy plus 3 for all real xy. Now for this first function, we see it is 2x plus 3 and right hand side is also of the form 2fx plus 3. So first we'll find its fixed point. So we'll take s equals 2s plus 3, or s will be minus 3. So our fixed point is minus 3. And for the right hand side also, we'll get the same fixed point, s equals minus 3. Now what we'll do is we'll recenter this function. So we'll take our input as u equals x minus s, and s here is minus 3. So it'll be this u is x plus 3 or x equals u minus 3. And then we'll shift the output also. We can shift the function by gu equals f u plus s minus s. So in this case, it'll give us gu equals f u minus 3 plus 3. And we'll use this definition to get fx later. So fx will be gx plus 3 minus 3. Now we'll change this first equation into scaling structure. Now in this f 2x plus 3, we'll subtract s both sides. So it'll be f2x plus 3 plus 3, and it'll be 2 fx plus 6. Now x is u minus 3, so it'll be f 2u minus 3 plus 3, and it'll be 2 f u minus 3 plus 6. Now f u minus 3 plus 3 is gu. So this is your g2u, and here we take 2 common. This is f u minus 3 plus 3. It is 2gu, which is a scaling function. Now, if we transform this second equation, we can write fx plus y plus 3, it is fx plus fy plus 3. Now, if we add 3 both sides, then we can write f x plus y plus 3 plus 3, it is fx plus 3 plus fy plus 3. Now, if we write this for our shifted inputs, we'll take u as x plus 3 and v as y plus 3. Then gu is fu minus 3 plus 3, and fu minus 3 is simply fx. So this is fx plus 3, and the same way gv will be fy plus 3. So this becomes gu and it becomes gv, and fx plus y plus 3, it becomes f u plus v minus 3 plus 3, and f u minus 3 plus 3, it is gu plus v. So this left hand side is g u plus v equals gu plus gv, which is additive Cauchy, and since f is continuous, this g is going to be continuous, which implies gu is of the form cu. And if we put it in this first equation, g2u will be 2cu and will be equal to 2cu. So this solution, it satisfies this equation 1. Now we'll find fx. So basically fx is gx plus 3 minus 3, and gx is cx. So it will be c x plus 3 minus 3, or simply cx plus 3c minus 3. So this function fx, it is given by cx plus 3c minus c. Let us take a similar question. Suppose a function is defined on R to R such that f3x minus 2, it is 3fx minus 2, and we are given fx plus y minus 1, it is fx plus fy minus 1. Now for this first equation, s equals 3s minus 2. We'll get s as 1. That means this u is x minus 1 and v is y minus 1, and we'll let gu as f u plus s minus s, and for the end we let fx as gx minus 1 plus 1. Now for this additive equation, we can write f x plus y minus 1, and we'll subtract 1, it'll be fx minus 1 plus fy minus 1, and we'll put x as 1 plus u. So it'll be f u plus 1 minus 1 plus f v plus 1 minus 1, and here it'll be u plus v plus 1 minus 1. Now f u plus 1 minus 1, it is g u plus v. So this is g u plus v, and will be this g u plus gv, which is additive Cauchy, and from here we get gu equals cu. So that's our first result. This first equation, f 3x minus 2 equals 3 minus 2. Now we subtract s. So it will be f 3x minus 2 minus 1 and it will be 3 fx minus 1. Now x is u plus 1. So it will be this f 3u plus 1 minus 1 and this is 3 f u plus 1 minus 1 and f u plus 1 minus 1 is gu. So this is 3 gu and this is 3u. Now this solution, it satisfies the scaling equation. So gu is cu, and once we have gu, we can write fx as cx minus 1 plus 1. So your function fx will be cx minus c plus 1. And that is the answer to this question. So this is how we use linearization to solve functional equations.